Hello everyone, myself Rajdeep Saikia. The topic I have chosen for my BTech final year project is design of a MOSFET-based low-noise variable gain amplifier for wideband 5G applications under the supervision of Mr. Manoj Sharma sir and Professor Kandrapurna Sharma sir and under the co-guidance of Dr. Surjit Tekka sir. So these are the outlines of my presentation. So as we have entered the 5G communication era, there is a need of new transmitters and receivers that are capable of 5G communication because 5G network contains high speed, high bandwidth, and high data rates, and it also uses millimeter wave spectrum. So in a receiver, a low noise variable gain amplifier is an important part. It can amplify very low power signals without significantly degrading the signal to noise ratio, and it can also vary its gain depending on the applied control voltage. So these are the papers I have taken help for my project. So, although various types of 5G receivers are being deployed, there are researches going on to develop a receiver that can work better than the current receivers. So we have initiated the propose to design a low-noise variable gain amplifier for wideband 5G applications that have high bands of frequency, tunable gain, and a very less amount of noise. So the design objectives are a wideband design with acceptable noise figure, high frequency bands, and gain tunability. So, as we know, most of the low noise amplifier designs does not support variable gain. So, if we can achieve variable gain, then the amplifier will be more versatile with the contemporary technological standards and enhancing the noise figure without compromising the gain at high frequency bands will give better performance. And area efficiency is another aspect that needs to be addressed. Reducing the area will decrease the cost of manufacturing. So this is a block diagram of a super heterodyne receiver, and this is a block diagram of a basic low noise amplifier which contains input matching stage, gain stage, output matching stage, and a feedback network. So in project phase one, I tried to design a low noise amplifier, but as we know, uh, a differential amplifier is a basic building block of a low noise amplifier. So first I tried to design a single stage differential amplifier, and these are the transient response and AC response of the single stage differential amplifier. After that, I tried to design a double stage differential amplifier, and these are the transient response and AC response of the double stage differential amplifier. And then I tried to design the low noise amplifier, and these are the transient response for different inputs of the low noise amplifier. And then I tried to analyze the noise figure of the low noise amplifier. So the noise figure of the low noise amplifier is 2.08 to 2.4 dB. And then I tried to change the capacitor values of the low noise amplifier to 10 femtofarad, and then the noise figure is achieved as 2.55 to 3.5 dB. And then I tried to change the length of the MOSFETs to 500 nanometer, and the noise figure is achieved as 19.3 to 20.95 dB. After that, I tried to change the width of the MOSFETs to 20 micrometer, and the noise figure is achieved as 4.58 to 4.678 dB. After the noise figure, I tried to analyze S parameters. So basically, there are four S parameters: S11, S12, S21, and S22. So the value of S11 is minus 15.7 to minus 12.8 dB. And like the noise figure analysis, I tried to change the capacitance to 10 femtofarad, and the S11 is achieved as minus 0.11 to minus 10.5 dB. Again, changing the length to 500 nanometer, the S11 is achieved as minus 1.62 to minus 3.58 dB, and changing the width to 20 micrometer, the S11 is achieved as minus 4.5 to minus 3.658 dB. The value of S12 is minus 102 to minus 63 dB, and changing the capacitor value to 10 femtofarad, the value of S12 is minus 119 to minus 61 dB. And when the length is changed to 500 nanometer, the S12 is achieved as minus 101 to minus 64 dB. And changing the width to 20 micrometer, the value of S12 is achieved as minus 97.5 to minus 58 dB. The value of S21 is 11.1 to 9.7 dB. The value of S21 for capacitor value of 10 femtofarad is 9.8 to 6.45 dB. Changing the length to 500 nanometer, the value of S21 is achieved as minus 20.18 to minus 20.6 dB. And the value of S21 for width of 20 micrometer is 2.26 to 1.53 dB. The value of S22 is minus 7.07 to minus 6.71 dB. Changing the capacitor value to 10 femtofarad, S22 value is achieved as minus 4.15 to minus 7.9 dB. Changing the length to 500 nanometer, the value of S22 is achieved as minus 3.54 to minus 4.8 dB, and the value of S22 for width of 20 micrometer is minus 4.79 to minus 4.6 dB. So these are the values of the parameters when I change the capacitor value from 1 femtofarad to 100 picofarad. So from the table, it can be seen that for the capacitor value of 1 femtofarad, the noise figure remains equal to the original value, but for other capacitor values, the value of noise figure increases. For all the capacitances, the value of S11 is higher than the original value. For 10 picofarad, S12 is higher than the original value. For 100 picofarad, S12 is equal to the original value, while for other capacitor values, the value of S12 decreases. For all the capacitances, the value of S21 is lower than the original value. For all the capacitances, the value of S22 is higher than the original value. So these are the parameter values for different length of MOSFETs. For the length of the value of noise figure is higher than the original value. For all the lengths, the value of S11 is higher than the original value. For all the lengths, the value of S12 is nearly same. For all the lengths, the value of S21 is lower than the original value and the value of S22 is higher than the original value. So these are the parameter values for different widths of the MOSFETs. For all widths, the value of noise figure is higher than the original value. For all widths, the value of S11 is higher than the original value. For all widths, the value of S12 is higher than the original value. The value of S21 is lower than the original value, and for all the widths, the value of S22 is higher than the original value. So the limitations of this design low noise amplifier is the gain is not variable, frequency is low, which is not compatible for 5G applications, and there are a large number of components, which also increases the cost of manufacturing. Therefore, in project phase 2, I tried to design a variable gain amplifier using gate picking technique. So these are the transient responses of the variable gain amplifier designed using gate picking technique. In figure A, you can see the transient response for control voltage of 100 millivolt. In figure B, you can see the transient response for control voltage of 900 millivolt. In figure C, you can see different outputs for control voltage of 1 millivolt to 900 millivolt. So the 3 dB bandwidth of this circuit is 131.917 gigahertz, which is compatible for 5G applications. For control voltage of 1 millivolt to 900 millivolt, the range of gain is 4.056 to 0.039 dB. For control voltage of 1 millivolt to 900 millivolt, the noise figure is 12.549 to 12.962 dB. So in this circuit, you can see that the noise figure is greater than 10 dB, which impacts on the output of this circuit. So I tried to design a variable gain amplifier using current steering technique. And these are the transient responses of the current steering feature circuit for control voltage of 100 millivolt. In figure B, we can see that the transient response for control voltage of 900 millivolt. In figure C, we can see the different outputs for control voltage of 1 millivolt to 900 millivolt. So the 3 dB bandwidth of the current stream feature circuit is 60.151 gigahertz, and for control voltage of 1 millivolt to 900 millivolt, the range of gain is 3.755 to 1.64 dB, and the noise figure is 10.167 to 24.199 dB. So we can see that the 3 dB bandwidth of this circuit is lower than the previous circuit. Therefore, I tried to connect two NMOSes at the input parallelly, and I replaced the two PMOSes, M8 and M9, with two NMOSes. And then I analyze the transient response of the circuit. So we can see in the figure A, the transient response for control voltage of 100 millivolt. The signal is very much amplified, and in the figure B, we can see the transient response for control voltage of 900 millivolt. And in figure C, we can see the control voltage for control voltage of 1 millivolt to 900 millivolt, the different transient responses. So the 3 dB bandwidth of the proposed VGA circuit is 149.109 gigahertz, which is compatible for 5G applications. For control voltage of 1 millivolt to 900 millivolt, the range of gain is 5.69 to 3.755 dB, and the noise figure is 8.488 to 24.609 dB. So I tried to compare the results of the proposed circuit with the other circuits that are gate picking VGA circuit and current swing VGA circuit. So from the table, we can see that the gain of the proposed VGA circuit is 5.69 to 3.75 dB, which is higher than the other circuits. The 3 dB bandwidth of the proposed VGA circuit is also higher than the other circuits, and the noise figure is uh, lower than the other circuits, which gives a better performance. And then I tried to compare the parameters with other state-of-the-art designs. So from the table, we can see that the proposed VGA circuit has a better gain and higher 3 dB bandwidth and a lower noise figure than the other circuits. So in the conclusion, we can say that in the transient response, it can be found that the output is amplified for control voltage of 100 millivolt to 900 millivolt, and the amplification reduces when we increase the control voltage. From the gain versus frequency graph, the 3 dB bandwidth is achieved as 149.109 gigahertz. From the gain versus control voltage graph, the range of gain of the circuit is achieved as 5.69 to 3.75 dB, and the noise figure for the design circuit is 8.48 to 24.6 dB. So the limitations of this circuit is the range of gain is 5.69 to 3.75 dB, which can be increased for better performance and better amplification. The noise figure obtained as 8.48 to 24.6 dB, but though it provides a good output, but if we can reduce the noise figure, we will get a better output. And as there are 9 NMOS transistors, it takes a large area, and if we can reduce the number of transistors, it will also reduce the cost of manufacturing. For future direction, for better performance, the frequency range can be increased so that it can use for a large bandwidth. The range of gain can be increased for a better performance. The noise figure of the amplifier needs to be reduced, and decreasing the number of transistors will reduce the area of the circuit, and it will also reduce the cost. So these are the references. Thank you.